Okay, so now that we are at the end of the unit on gases, basically, I'm going to tell you the thing that actually governs every single gas law and gas property that we have been talking about. And it's a thing called KMT, or Kinetic Molecular Theory. And it's basically a lot of common sense that goes right back to what you would imagine about gases, even just from very simple particle diagrams from earlier years in chemistry and in middle school. So there's a couple of things in here that we know are absolutely true. And it's the second postulate here, and it's the fourth postulate. So gas particles are in constant motion, colliding with walls of a container to create pressure. All right, so we have been talking over and over again that collisions generate pressure. That's what pressure is. So it is the constant motion of gas particles, which again is different from solids and it's different from liquids. That is creating pressure. Solids and liquids don't necessarily create pressure in any meaningful way because they don't have that constant motion. So the other thing, average kinetic energy of gas particles is directly proportional to the temperature in Kelvin. So otherwise, you can think that the temperature, again, is a measure of average kinetic energy. So two substances at the same temp will have the same average kinetic energy. That's going to be important when we think about the next video talking about diffusion. Okay, so what about these other two, number 1 and number 3? Well, let's look at number 1 first. The volume of gas particles is negligible compared to its space. Okay, that's not quite true, because what we do know is gas particles do have space. Do have space, just not very much. So you can run into problems when you are shoving gas particles together so that the space that they take up matters more, or when you just have tons and tons of gas particles and they start bumping into each other. So you have to look at this this comparison between the volume of the gas particle and the space inside the container, right? So as long as there's a big difference between those two things, then number 1 can pretty much be true. But if you start having gas particles taking up more and more of the container, well, you're starting to get dangerously close to being a liquid. And that is going to make the kinetic molecular theory and all of this gas behavior fly out the window. The other thing that is not true, gas particles neither attract or repel one another. This is blatantly not true. And the way we know this is not true, it's because all particles have what we call IMFs, right? Intermolecular forces. This is that stickiness that we talk about sometime, or attractions between things. So that happens because of positives and negatives, right? That's going to happen. So stickier things are going to be more problematic for kinetic molecular theory than things that are not as sticky. Things that are not as sticky are going to behave more the way everything else in this section has said they would. So what do we do about this? Well, we need to know how to mimic ideal conditions, right? We need to get there. So we need to overcome the volume issue, and we need to overcome the stickiness issue. Okay, so I want to look at this graph, and this is a graph right from one of the other packets that I gave you. And you'll see here, this dotted or this solid line here, That is ideal behavior, right? That's what it should be. This is, if KMT is totally true, you would be on that line. And you can see that these other gases, well, they're not exactly on that line. They're a little bit off. Now, the gases being used here are noble gases. Okay, and that's important because noble gases are not sticky. So here in this graph, we're just going to isolate and look at this volume issue. So looking on this X and Y axis, where are we closest to this line? Well, our gases over here are the closest to this ideal behavior. So what are we seeing for volume and pressure there? Well, we're seeing large volumes, okay, and we're seeing low pressures. And that should make sense because a low pressure is going to allow the particles to move through space. So if they're moving through space, then they're kind of negating this volume issue. So one of the ways you want to mimic ideal conditions is to have a low pressure, because a low pressure will lead to a large volume. Okay, so that's one thing, low pressure. That's super important. Okay, so let's look at the other factor, which is the stickiness. Okay, so this graph can tell us about stickiness. Now, we haven't gone over quite everything we need to in order to talk about stickiness or IMFs, but basically what we are talking about here is something called polarity. And these two things right here are polar, HCl and NH3, and the H2 and the NO2 are not polar, all right? So which of these is going to be closer again to my solid line? Well, I don't think that's hard to see at all. Non-polar is just like the ideal, right? No sticky. So that is already taken care of the whole stickiness factor. But these other things, these polar things, well, that's a problem. They definitely do have a large amount of deviation from ideal, and there's no getting away from it. It doesn't really matter, the pressure or the volume are not overcoming sticky. Okay, so pressure and volume can't overcome sticky. So how do we overcome sticky? Well, you got to think about it. Stickiness means that they are passing by each other, right? So I have a particle going in this direction and a particle going in this direction. And as they come near each other, right, they get sticky right here. All right, that's what we're talking about. So the way to keep them from being sticky is to make them faster. And if you can make them faster, you can overcome the sticky. Well, how do you make gas particles faster? It has nothing to do with pressure. It has nothing to do with volume. So the only other variable left that we have at our disposal is temperature. So what should we want to do to make our particles go faster and overcome the sticky in terms of temperature? Do we want a low temperature or a high temperature? Well, high temperatures equal faster speeds equal less sticky. So to recap, what we are looking for is a large volume, a low pressure, a high temperature, and a non-polar gas are all going to mean that we get close to ideal and KMT being true. That's what we're looking for.